Hello, in this section, I will go over Rolle's theorems and determine the C-value if Rolle's theorems can be applied. So we are definitely doing Rolle's theorem. So what is Rolle's theorem? In simple English so what is Rolle's theorems? In simple English, between points A and B, there is a point C, and you can have more than one C value where there is a horizontal tangent. So I think, so let's say you had this upside parabola, right? And here's A and B. Here's point C. As you can see that it has a horizontal tangent at at the X value C. So that's what it really is. It's just, if you have a horizontal tangent at point C. Now you can have more than one C value, but in order for Rolle's theorems to be applied, or in order to find C, it has to apply three conditions. So let's talk about Rolle's theorem. Let F be continuous on the closed interval A to B. So it has to be continuous on the closed interval A to B, meaning there's no picking up your pencil, and differentiable on the open interval A to B, parentheses A to B, so that in order for it to be differentiable, there has to be no sharp terms, no cups. And also f of A equals f of B. Then there is at least one number, a C, in that A to B, such that f prime is C equals to 0. So this is what it means in the diagram. So first has to do with three conditions. So like I just said, continuous on bracket A to B, differentiables on parentheses A to B, and then f of A equals f of B. So let's do an example. So in the following examples, determine whether Rolle's theorems can be applied to F on the closed intervals bracket A to B. If Rolle's theorems can be applied, find all values C in the open intervals from parentheses A to B, such that F prime C equals 0. Okay. So on example 1, we have f of x equals x squared minus 2x in the closed intervals from 0 to. So first off, you might want to look, kind of draw it briefly, like draw a rough draft of x squared minus 2x. Well, I know that's a parabola. It's a concave up parabola, right? So it would look something like this. Wait, first let's find f of, so this is your A, here's your B. Let's find f of A and f of B. So f of 0 is 0 square minus 2 times 0, which is 0. And then f of 2 is 2 square minus 2 times 2. That's 0. So that's 0. It has a y value of 0. And then at 2, it also has a y value of 0. And I know it's a so it would look something like this. Roughly, right? Now, does it can we apply Rolle's theorem? So is it differential? Is it continuous on bracket A to B? Yes, it is continuous. There's no there's no holes. There's no picking up the pencil. Is it differentiable on the intervals parentheses A to B? Yes, because there's no sharp terms, there's no cusps, so it is differentiable. And then does f of A, the third rules, does f of A equals to f of B? Yes, right? Because if you plug in 0, you get a y value 0, and when you plug in 2, you get a y value 0. So it's true, f of A does equal to f of B. So yeah, we can definitely can use Rolle's theorem. So let's find the C value where there has a horizontal tangent, and I think there's only one, because I think this will be our C value. and then this will give you the horizontal tangent of 0, right? So C is technically an x value. So how do we do that? We're going to take f prime, which is 2x minus 2, and then set that to 0. And then try to just solve for x. So you're going to add 2. Okay. So what that means is at the x value 1, so our c value is 1. So at c at 1 right here, the y value will give you a horizontal tangent. Okay. So you could say, or friend also could say f prime of 1 equals to 0. Let's move on to example 2. So we have f of x equals x minus 1 times x minus 2 times x minus 3 in intervals of 1 to 3. So I think it is continuous and differentiable because it is a polynomial, right? It is a polynomial, so there is definitely no there's no sharp terms, there's no open circles. So so now let's find f of a, f of b. So yeah, if here let's first find f of a, f of b. So f of 1 is going to be 1 minus 1, 1 minus 2, and 1 minus. This is just going to be 0 because 1 minus 1 is 0, so that's just going to be 0. And then f of 3 is going to be 3 minus 1, 3 minus 2, 3 minus 3. This is also going to be 0. So we can say that f of a does equal to f of b. And then we can also say it's differentiable. On bracket 1 to 3. And then it's also differentiable. I mean, it's continuous on bracket 1 to 3, and then it's differentiable. On open intervals 1 to 3. So if you don't believe me, you could just put that up in decimal, or you could just, here, I'll draw a rough draft. So we said that f of 1 is 1, 2, 3. So f of 3 has a y value 0, and f of 1 has a y value 0. And then if you find the y-intercept is like at -6. 6. So this is what it would roughly look like. It is a polynomial, and it's an odd degree polynomial. So we know it rises to the right and increases to the left. So it would look something like this. Roughly, right? So how much C, we can use Rolle's theorems, but how much C values would we have? So where is there a horizontal tangent of 0? So we have one right here. So this could be like your C1. And then you also have one right here. So you can also, so this could be your C2, right? So it looks like we have 2 C values. So Rolle's theorems does apply. So now let's find the C value. So what should we do? We should FOIL it out, right? So if you FOIL it, what I would just do it one by one. So I would FOIL this out and then FOIL that out. So that would be f of x. Wait, let me just write it out again. X minus 1, x minus 2, x minus 3, right? And if you FOIL this, let's just FOIL this part and then FOIL the last part. So that would be when you FOIL this out, you're going to get x squared minus 3x plus 2. Then you're going to FOIL out the x minus 3. So that would be when it all comes together, it'd be x cubed minus 3x squared minus 3x squared plus 9x plus 2x minus 6. And then if you clean it up, it would be f of x equals to x cubed minus 6x squared plus 11x minus 6. And then just take the first derivative, f prime of x is going to be 3x squared minus 12x plus 11. And then we're going to set this to 0. So unfortunately, you can't do bottoms up factoring. It won't work. I tried it. So I think we could just do quadratic formula, and I think also completing the square will work. So our a value is 3. My b value is negative. I'm going to just do quadratic, and c is 11. So you could say that c equals to 12 plus or minus 144. Okay, and then when you simplify the square root of 12, you get so yeah, when you simplify this, you can get you could factor out a 2, so it would be like plus it would be 2, 6 plus radical 3 all over 6, and then the other one would be, if you take our 2, that would be 6 minus radical 3 all over 6. Now when you reduce the 2, your final c values would be 6 plus radical 3 all over 3, and then it's going to be c equals 6 minus radical 3 all over 3. So we, based on the graph, we do definitely have 2 on our intervals. So those are your c values. So you could say that your final answer can be said c prime of 6 plus radical 3 all over 3 equals to 0. And then the other one would be c prime 6 minus radical 3 all over 3 equals to 0. Okay, so these are your 2 c values. Okay, so let's do example 3. F of x equals 2/3 minus 1 on the intervals from negative 8 to b. So let's see if Rolle's theorem applies. Well, let's just graph what it looks like. So if you put this in Desmo, it would look something like this. Right? And is it continuous from bracket negative 8 to 8? I guess so, it is continuous. I mean, there's no holes, there's no picking up a pencil, so yes, continuous from bracket negative 8 to positive 8. Now, is it differentiable? No, because there is a cusp right here. So it's not differentiable. So I guess we don't have a C value. So uh Rolle's theorems can't, you could say no C values. Since Rolle theorems cannot be applied. Okay, last one. So f of x equals x squared minus 2x minus 3 all over x plus 2. So it's noticed it's in a fraction form, so that's a big clue that it is a rational function. But it is still possible for a rational function to be that can be applied as Rolle's theorem. So if you want, let's kind of like make a graph of it. So this is a rational function. So what I would do is find the VA, the vertical asymptote. So to find the vertical asymptote, you set the denominator 0 and solve for x, right? And then to find the horizontal asymptote, notice it's top heavy. So you have what's called an oblique. So it's like a linear, a linear dashed line. So how do you find it? You do long division. So this would be x, right? So this would be x squared plus 2x, and then bring down the negative. So this would be negative 4x, bring down the negative 3, and then you need a minus 4. So it's a minus negative 4x plus 8. Okay. And then you have a remainder of 5. That doesn't matter. The remainder of 5 doesn't matter. So our oblique asymptote could be y equals x minus 4. So let's kind of draw it. I mean, you can put this in decimals if you want. And then you have an oblique asymptote. So you have an oblique asymptote at y x equals negative 4. So you have a y-intercept of negative 4. Okay. So 1, 2, 3, 4. Here's negative 4. And then you have a slope of positive 1. So 1, 1. So it's a, remember, it's a dash line. So make sure you use your dash. And then when you actually draw it, it would look something like this. I mean, sure, you could test points, but it would look something like this. Okay. And then so let's see if Rolle's theorem can be applied. So is it continuous on intervals bracket -1 to 3? -1. Yes, it is. There's no costs. I mean, there's no open circles, so it is. You could say yes, it's continuous from bracket -1 to 3. Is it differentiable from open intervals -1 to 3? Yes. This little curve isn't a sharp term. It's like so there's no sharp terms or costs. So we can say yes, it's differentiable from -1 to 3. Okay. Now what are we going to do? check if f of b equals f of b equals f of a. So let's see, if you plug in f of 3, what do you get? We get 3 squared minus 2 times 3 minus 3. Then it's going to be all over 3 plus 2. And when you put that in the calculator, you're going to get 0. And then f of f of negative 1 is going to give you that, and when you put it all in the calculator, you get 0. So you can, yeah, so definitely f of a does equal to f of b. So Rolle's theorems can be applied. So okay, we got to take the derivative of this rational function. So we're going to use the quotient rule, right? So if you recall, so let me write out my function again. And yeah, if you recall that the quotient rule is this, f prime of g minus g prime of f all over g squared, right? So our f is what? X squared minus 2x minus 3. So f prime would be 2x minus 2, and then g is x plus 2. So g prime would be 1. Okay. So then we just, so it's going to be f prime of x equals to, it's going to look something like this. It's going to be 2x, oops, 2x minus 2 times x plus 2 minus, I'm going to put a bracket, and then it's going to be g prime, which is 1, x squared minus 2x minus 3, parentheses bracket, all over g squared, which is x plus 2 squared. And when you FOIL out, clean it up a little bit, it would look like this. And then clean it up one more time, and you'll get okay. So then what we'll do is set this to 0. Or 0 over 1. And then when you cross multiply, this is going to be x squared plus 4x minus 1 equals 2. And then when you cross multiply, this is good at x plus 2 squared times by 0 is 0. And what are we going to do? We will doesn't factor, you can't do simple factoring, so we'll probably have to do quadratic formula. So a equals 1, b equals 4, c equals to -1. Whoops. So it's going to be c equals opposite of b, which is -4. B squared is 16 minus 4. Okay, so when you, I'm not going to do this because this is algebra. When you clean this up, you should get, you're going to get 2 c values. You're going to get actually 1, because if you look in our graph, our intervals is from -1 to 3, and we only have one that has a horizontal tangent of 0, right? We can't use this section. So our C value is going to be -2 plus radical 5. And then the final answer can be expressed as f prime of -2 plus radical 5 equals to 0. Okay. So that wraps it up for this section. Thank you. Bye-bye.